Okay, you guys can pause the video if you want to reread that, but at this point we're just going to go ahead and take the information from the beginning here, and it's just saying that the key piece of information is each zombie can turn 3 humans per day. So what that means is if you have 5 zombies, you're just going to multiply 5 times 3, you're going to get 15. 15 times 3, you're going to get 45. 45 times 3, you're going to get 135. And you're just going to keep repeating that process. So I'm going to pause the video and fill the chart out, and we'll see how that compares to yours. Okay, so look at question 1. What patterns of growth? Growth means something is increasing. Do you notice in the number of zombies turned? And we already answered that from the beginning of the intro to the project here, that you're just multiplying the information in the table by 3 each time. And you can see that there. That was pretty simple. Okay, question 2. What would this data look like on a graph? Sketch the graph over there, over the sketch a graph of the data for days 1 through 10. So at day 0, they started out with 5 zombies. 5, and if you notice on the y-axis right here, I've counted by 50s, 50, 100, 150, 200, 250. And we're talking about in terms of thousands because that was the range that was in the table. So if 0 day was 5 zombies, that's pretty much nothing. And then we said on day 1 that was 15, that's pretty much nothing. And then 45 is pretty much nothing. And 135 is pretty much nothing. And so I'll have to go back to my table here. So if I go back to the table, and then day 4, 405 and 1215, so we'll do that. 405 is pretty much nothing. 1215 is pretty much nothing. Day 6 is 3,000s. Now we're starting to get into the thousands. You'll notice about right here we don't get close to the 50,000 mark until between day 8 and 9. So it's still going to be really close to that 0 line there on the x-axis. So you'll see that the data is going to be really close here. So I'm going to pause the video. I'm going to plot the rest of those points here. Okay, so if you look at your graph, this is called an exponential graph. And what that means is it starts off really small and then all of a sudden it just shoots up really quickly. So let's look at our questions here. What would this data look like? We have that, boom. From the table or the graph, how many zombies are turned on day 10? Well, from the table I believe is right at around 295,000. I'm just estimating because now we don't have to flip back and forth. What would you have to multiply this number by to get the number of zombies created on the 11th day? We said you're just going to multiply that times 3. It's not asking how many zombies are on day 11, just what do you multiply by? How would the entire table, here we go, and this is a typo here on letter C, how would the entire table change if instead of starting with 5 zombies, we started with 1 zombie? Well, what change is you would have to go through and just kind of make a table. If you start with day 0 has 1 zombie. Day 1 has 3 zombies. Day 2 has 9 zombies. And if you compare that to the other table, and I'll just make a small one here. Day 0 had 5 zombies. Day 1 had 15 zombies. So you see that this new table would actually start off with less. So you would have a lesser amount of zombies. So the graph would actually be a little bit below this one. And so you would have less zombies, of course. How long would it take now we're looking at letter D, how long would it take now for the zombies to take over the world? I did give you a hint to go over and answer, let's clear this here, answer question 4 first before we answer question 3D, because we can use the equation from 4 to answer this question. How long would it take? So let's jump down to question 4. Which of the equations below correctly models the information from the table is what it's asking. It's actually this equation here, y equals 5 times 3 to the x power. And if you look right here, I already have that equation in the calculator. And if I go back to my table, you will see that the data matches up, like day 4, 405, day 5, 1215. So that is the correct equation there. So now that I have this equation, if we go to the question, 3D, we're looking right here. How long would it take to reach almost 7 billion zombies? the entire population. So we're looking in the Y column here, and we're just going to scroll down until we see about 7 billion. Now, you have to go back to scientific notation. The way I would write 6,975,000,000, that would be 6.975, and the calculator is going to go e to the 9. And so I need to make sure that I'm e to the 9. Well, if you look right here, it's going to be in between 19 and 20 days. So we'll say between 19 and 20 days. That's when we all become zombies. Question 5, what does the unknown variable x represent in the equation? The unknown variable represents the days. Now, for the project's sake of this, we skipped 6 and 7, so we're not going to address that information. So let's go to the next page here. Within 3 days of the initial attacks, a group of scientists quickly began working to find an antidote. Within a few short weeks, they were successful. But what the information here in the table is saying, or the intro, it's only 15% successful. So we need to make a table. So the way this works is you're going to take the total zombies. We're all zombies now. We're going to multiply this times 15%. And whatever answer we get right here, you need to take that answer and subtract it from the information from the table, because it's not asking how many people did we cure. This would be the cured number of people. It's not asking for this number, it's asking how many zombies remain. So we have to subtract that. And so, if I go through here, we'll start with 6,975,000,000, and then we are going to multiply that times 15%. We're going to get that number there. And then what we're going to do is we're going to take 6,975,000,000, and we're going to subtract it. 2, 3. I need one more 0. We're going to subtract that from the. We're going to take our answer and subtract that. Excuse me. Had that backwards. And this 5,928,750,000. And then you're just going to repeat this process over and over again. But I want to show you a trick. If the number of people cured is 15%, then the number of people that are not cured is 85%. So think about this. If it works 15% of the time, it fails 85% of the time. And 85% would be the number left over. Watch. 6,975,000,000 times 0.85. And this will tell me how many zombies are remaining. It'll automatically do that. So I'm going to pause it, fill this information out, but I'm going to use 85% instead of the 15, because I'm not worried about how many people are cured. I'm worried about how many zombies are left. Okay, so you see the idea with the table here. Look at number 8. What patterns of decay? Decay means something is decreasing. And we already picked up the pattern. The pattern is that it's decreasing, but the number of zombies remaining is still 85% of the time. That's pretty simple. What would this data look like on the graph? So we're going to start here. Let's see here. We're going to start here. And I'm just going to estimate this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, day 10. And if you look up in your data, it was in the billions, right? So we're going to do 1, 2, 3, 4, 5, 6, 7 billion. And so on day 0, we had about 7 billion. And then what happens is the graph ends up doing something like this, if you did this correctly. Something similar to that. And then it says write an equation to model the pattern in the data. Okay, I gave you that information on the help page. It looks like this: 6,975,000,000. And then 1 minus 0.15 to the x power. But remember, algebra, we want to simplify. So instead of rewriting this entire number again, it would just be 0.85. Right, and then you would put the 6 number right here. So this would be your equation. And you can see that pattern, that 0.85 built in right there. Number 11 is a little tricky. It says, at this rate, how long will it take the scientists to completely turn all the zombies back into humans? Well, if you go back to your graph, it looks like this. and you'll see that this is 0 on the x-axis right here. This line will get really close to 0, but it'll never hit it. Now, if I go to my table on the XY table on the calculator, it's going to, if you keep scrolling down, eventually the calculator is just going to give up and just say it's 0, because the calculator is not going to do this. It's not going to go all the way out that many decimal places. It's going to go, you know what, that's close enough to 0, we're just going to 0 it out. So they will never be able to really cure the entire population, because you will have a fractional amount of people. I know that kind of sounds weird, but to cure everybody would have an exact number of 0. This line right here that the graph will never hit is called an asymptote. It's an imaginary line that the graph approaches, but it'll never touch. And then number 12, what similarities and differences do you notice in the equations developed? Well, you'll notice that in the equations that we developed, the x was in the exponent, right? So you had some information and then the x was up here, where you guys are used to seeing the x like this. Well, not with exponentials. So if you get a graph that's going to go up like this, or one that goes down like this, chances are that x is going to be in the exponent part of the equation.